Chapter 2, Section 3, Acceleration. So velocity and acceleration. Acceleration is a rate of change of velocity. So in other words, how fast is an object speeding up or slowing down? And this occurs when an object changes its speed, its direction, or both, because velocity has both a speed and a direction. So if I change either one of those, then I'm changing velocities and therefore I am accelerating. Acceleration doesn't necessarily mean speeding up either. Since velocity has a direction, acceleration also has a direction. But since acceleration doesn't necessarily mean speeding up, it could also mean slowing down. It could also just mean changing directions. So types of acceleration. So if you're speeding up, the acceleration and velocity are in the same direction. So in this case, both to the right. If you're slowing down, acceleration and velocity are in opposite directions. So your velocity is to the right, but your acceleration is to the left, so you'd be slowing down. Changing directions. Acceleration is in some other direction. In this case, it's perpendicular to velocity. So your velocity would continue in this direction, but the acceleration would cause it to turn. So if you have acceleration in a different direction, you have an object that is turning. Speed time graphs and acceleration. Speed time graphs can provide information about acceleration if object is traveling in a straight line. So if the object is traveling in a straight line, we can get information about acceleration. The slope of a velocity time graph or a speed time graph is equal to acceleration. So we look at this as an example. Here we start off at rest, and then we speed up as we're pulling out of the driveway. Continue at a constant speed for a bit, and then we slow down to stop at a red light. While we're stopped at the red light, we're not moving. So our velocity or speed is 0 for that time period. Then we speed up again, move at a constant speed for some time, for a couple minutes here. Then we slow back down to enter a parking lot. Then we travel at a constant speed around the parking lot, and then we park and we stop. So this is a speed time graph, and the slope is equal to your acceleration. So if you have a positive slope, you have positive acceleration. If you have a negative slope, you have a negative acceleration or slowing down. So calculating acceleration. So acceleration is the rate of change in velocity. So velocity is in meters per second. Time is in seconds. So acceleration ends up being in meters per second squared. So again, change in velocity or velocity in general is meters per second divided by seconds. So you end up with seconds on the bottom twice, so it's seconds squared. And a negative sign means that it's in the opposite direction. So the acceleration will be in the opposite direction. So we have acceleration is change in velocity. Change in velocity is our final velocity minus our initial velocity. We put them in that order because if our final velocity is lower, then we end up with a negative number indicating a negative acceleration. If our final velocity is higher, we end up with a positive number and therefore a positive acceleration. So it's our final velocity minus our initial velocity divided by t, or divided by time. So motion in two directions. So you have to discuss motion in each direction separately. So if an object is changing direction, the acceleration is not in the same or opposite direction as the velocity. In a lot of cases it's perpendicular. So in this case, we have sort of an object maybe rolls off a table. It's got a velocity to the right, and as it rolls off the table, it starts to accelerate downward due to gravity. So you have to talk about the horizontal acceleration and velocity and the vertical acceleration of velocity separately. Circular motion. So think about a horse on a carousel. You have a circular path. So the horse goes around the circle. The red lines indicate our velocity, and the blue line or blue arrows represent our acceleration. So you have constant speed but changing direction. So you do have acceleration here. We call this centripetal acceleration, and that is the acceleration toward the center of a curved or circular path. Projectile motion. Projectiles are anything thrown or shot, and these follow a curved path. So if you shoot an arrow, for example, it doesn't go straight forever. As soon as it leaves the bow, it starts to drop. Or if you throw a baseball, the same thing, it starts to drop. So when you throw something, the horizontal velocity is constant after it leaves your hand, but then gravity starts to accelerate the object downward. That's why if you're shooting a bow, you got to aim higher than your target. Or if you're throwing a baseball, you got to aim higher than your target. Same with a football or anything else. Any kind of thrown object or object that's shot, it curves downward. So if you're aiming for a specific target, you have to aim higher than that target because it's eventually, as it travels, it's going to drop. And this picture kind of shows this constant velocity once the rubber band leaves her finger of 2 meters per second to the right. But then we have this velocity downward due to gravity that continues to increase. Starts off at 0, then goes to 0.5, then goes to 1 meter per second. So throwing versus dropping. So a thrown object will fall at the same rate as a dropped object. They have the same downward acceleration. So that acceleration is due to gravity. So gravity is pulling down equally on both objects. So the red ball and the blue ball in this picture are both being pulled down by gravity. The only difference is the red ball drops straight down because it doesn't have any horizontal velocity when it falls. The blue ball, on the other hand, has a horizontal velocity to the right. So when it falls, when it leaves the edge of the table, gravity starts to pull it down, but it's also still got this velocity to the right. So it kind of travels in this arc. But if you notice, at each interval, the ball is at the same location. So they're falling at the same rate. One other thing to notice too, you kind of see acceleration here in the picture in the spacing of the balls here. So this actually is fairly close together because it hasn't picked up a whole lot of speed. Picked up a little more speed, more speed, more speed. You can see this acceleration as this gap between the two pictures increases. What they've done here is they've taken a strobe light and just taken a series of picture or one picture with the strobe light on, and the strobe light hits the ball and bounces off of it, and that's where you can actually see the ball. So anyway, you can kind of see this acceleration as the spacing between them increases. So amusement park acceleration. We don't really feel velocity so much, we feel acceleration. So if you're sitting in a car traveling at 70 miles per hour, you don't necessarily feel that. Now, if you slow down suddenly because somebody stops in front of you and you slam on the brakes, you feel that. You feel that your body continues to move forward as the car is stopping. Or if somebody's sitting still, if a car's sitting still and then somebody hits the gas really hard and the car speeds up quickly, you feel like you're being pushed back into the seat. That's acceleration. If you are turning a corner, you feel that acceleration as well, like you're going towards the door or towards the center of the car. So we don't feel velocity so much. We feel acceleration more than anything. In fact, they talk about G-forces in wrecks or in rocket launches and stuff like that. When they start talking about G-forces, that's acceleration that you're feeling, or that the people are feeling. Anyway, amusement parks are designed to create a feeling of danger by accelerating the rider in different ways. So again, we take these sharp drops. So you have a sharp drop at the top of a hill where you accelerate downward due to gravity. You can have loops where suddenly you're accelerating downward and now you're accelerating kind of in towards the center of this loop as you're going around through here. We have sharp turns where you're accelerating towards the inside of the turn, and that all that goes together to create this amusement park experience where you feel like you're in danger, but you're really not. Even something as simple as the carousel we had earlier, as adults, we don't necessarily think that's too crazy, but as kids, that's an exciting kind of ride because you feel like your body's trying to go straight forward, but it's constantly wanting to curve because of the forces on the body and the acceleration.